Welcome to day two of Arize Observe. Today we have Anthony Goldbloom, who was one of the founders of Kaggle. Feel free to introduce yourself, Anthony. And I'd love to, I feel like there's a whole generation that would love to hear about Kaggle. And so tell us a little bit about what it was, what it is today, and just your maybe that initial journey too.
Yeah, totally. Well, to start off, my background is econometrics and statistics, and I feel like in the very early days of data science, my definition, at least, of a data scientist was somebody who knew more statistics than the average programmer and more programming than the average statistician. Now, Kaggle launched in before Kaggle, I had worked for the Australian government doing econometric forecasting, so forecasting GDP, inflation, and unemployment. But I very much met that definition where I was a hobbyist programmer. I used to use things like R and Python as opposed to MATLAB and some of the other more statistically focused tools. Used to read this newsletter, which I think is probably still around, called KD Nuggets, there was this very small community of people that did, sometimes it was called data mining, more so than machine learning. And I used to read those newsletters. And in those newsletters, they used to advertise every year there was a conference called KDD. And the KDD conference would have a competition attached to it called the KDD Cup. And so, like most academic conferences, you could get a spot at the conference to speak by submitting a paper, but they had this other track where they would put out a problem, and the top performers on that problem would get a slot at the conference. And I always thought that was very elegant, right? To measure the quality of somebody's contribution by having a human review their paper is somewhat subjective. I always thought the idea that you could run a challenge and evaluate whose algorithms were most accurate was sort of a very, very elegant way to divvy out spots at this conference. And at the time, I would say, I think now conferences like NeurIPS and CVPR have become I guess more prestigious, but at the time, KDD was a very sought after conference to get the opportunity to speak at. And so that really where Kaggle came from was bringing the idea of the KDD Cup into industry. We started running machine learning challenges. So we'd have companies like Allstate, the insurance company, or Ford, obviously the vehicle manufacturer, run challenges with us. So Allstate wanted to predict insurance claims. Who's going to crash their car? Very much a bread and butter challenge for an insurance company. And so they would put up their problem on the Kaggle website, and data scientists, machine learners would compete to build the best algorithm. And it was really, worked very well because we had some holdout set where we knew the answers, so we could evaluate people's performance against real data. And the winners would win prize money, and in exchange they would give the intellectual property to Allstate or whoever the host was. And certainly, I think Kaggle ended up being a very effective way for companies to discover new solutions. In Allstate's case, they were using techniques that were very common in insurance circles, actuarial techniques and so forth. And they learned about, I think it was gradient boosting machines won their challenge. And in the early days of Kaggle, the data scientists came from lots of different backgrounds like mine, econometrics, but computer science, bioinformatics, and really each of those disciplines had their own pet techniques. In econometrics, we're mostly using things generalized linear modeling, so things like logistic regression and so forth. The computer scientists were often using more decision tree-based techniques like random forest and a little bit of neural networks, some support vector machines. Bioinformaticians had their own set of techniques. And so the kind of magic of Kaggle in the early days was it brought all these different groups together to compete on the same challenges. And you could see objectively what would do well. And I can talk a bit, one thing we can talk about a little bit later is like the evolution of techniques from, random forest through the transformer-based models that we have today, and what sort of inflection points we had over time. But that was how Kaggle got its start. As the company grew, we added on more services. So we added on a hosted note. For those familiar with Jupyter notebooks, we added on a hosted Jupyter notebook. And initially, we saw people trying to share code in our forums, and so we thought, oh, why don't we give them an environment with a standard set of Python packages where they can easily reproduce each other's code. And so that's where the hosted notebook came from. And really, it was meant to be a support to competitions, but then we saw people starting to use it on non-competition data sets that sort of hack around our systems to bring in other data sets. And so then we launched a public data platform, which allowed anyone to upload their own data sets. And so three main components to Kaggle today are machine learning competitions, the hosted notebook, and the public data sets. And it's a community.
Yeah, and I feel like one of the things, I mean, a lot of us started on Kaggle, started building models and testing ourselves on Kaggle. I do think one of the things I noticed in my earliest days was just the result difference sometimes between when you build and when you submit. And so can you talk a little, maybe just highlight why you want to test blindly, why it's important to continue to test and compare people in a blind fashion, and how you grew from that, the importance of that in the beginning?
Yeah, totally. One really large problem in machine learning is something called overfitting. And what will very often happen is you'll train a model, and you might get really good performance on that model, and then you'll apply that model on a future data that hasn't come in yet, or some other sample, out of the same raw data set that doesn't perform as well. Now, what Kaggle used to do, which was quite clever, is we would have a leaderboard that showed people how they were performing, or what we do, or what they do. So I'm not there anymore, so I shouldn't say we. Is have a live leaderboard that shows how participants are performing in real time, so you can get a sense for what your performance is. But then what we do is we actually throw away all the test cases, on that live leaderboard, and we rescore people on a second test data set where nobody has had any feedback. And not only that, if you put in 100 submissions to the competition, you can only pick 2 that are evaluated on that second test data set. And something that we would see very, very often is you'd have, I don't know, somebody in, call it 9th place on the public leaderboard, and then when we switched over to the private leaderboard, they were in 100th place. And what had happened was they had overfitted to the public leaderboard, but they hadn't built an algorithm that generalized. And so it's a very powerful thing about Kaggle that the test data set is under lock and key, and so you cannot physically overfit. And I've always had this suspicion, very high fraction of people who do their first Kaggle competition have that dynamic where their public leaderboard score performance is much higher than their private leaderboard score. And it makes me think that when you have people building models, inside their companies, building research papers, where the test data set is not under lock and key, how many of those cases are we looking at models that are actually overfit and don't generalize well in real life? Just based on what we saw at Kaggle as to how often it happens, it makes me think that a very high fraction of the world's algorithms in deployment are actually overfit.
Yeah, and I think the interesting point there is just, and I think it's true independent of the new world of LLMs or anything we're doing, is you need to test yourself. You need to test yourself and have solid tests behind it that give you ideas of if what you're trying to do is working in your deployed scenario, similar to how you built it. And that kind of in the idea, in the kind of hinting on the new world stuff, can you talk about the evolution? You've seen so much in the last decade. What's been the evolution for you? What have you seen recently? And love to hear that story.
Yeah, so I'll go through the full history at least as I have seen it. As I said, in the very early days of Kaggle, you had all these different disciplines folding under this one data scientist job title,
Yeah.
and you went from people using a whole lot of random techniques to random forest became very clearly the dominant technique early on in Kaggle. It won everything. Then in 2012, there were two developments. There was an algorithm that people were excited about called gradient boosting machines that had nicer properties than random forest, but were harder to implement. And Tianqi Chen from the University of Washington built a really beautiful implementation of gradient boosting machines called XGBoost, which, by the way, is still the dominant way to train models on small structured data sets. It still dominates on small structured data sets, surprisingly. The other thing that happened in 2012 was, 2012 is often called the annus mirabilis for deep learning. It's the year Jeff Hinton and some of his grad students got a spectacular result on ImageNet. So ImageNet was a computer vision benchmark or challenge, not run on Kaggle, run by a Stanford researcher named Fei-Fei Li. And so that was, and what had happened was, for the longest time, people were, there was excitement about neural networks, but they never really, they had some successes. Like there was the famous digit recognition. I think it was used by the Postal Service to read zip codes, and people at the time thought, oh, they can read numbers, and look at all the amazing things neural networks are going to be able to do. But they never quite lived up to the promise. There were a set of academics, now very well known, Jeff Hinton, Jan LeCun, Yashua Bengio, who never lost faith and continued to iterate on those techniques. And in 2012, they had that breakthrough result on ImageNet, results of being able to train deeper neural networks on GPUs and so forth. And really, since 2012, what has happened in machine learning has just been breathtaking. So the first set of use cases were computer vision use cases, so classifying images. This image is a dog, this has a cat. Doing object detection, so being able to count Coke cans in an image, or things like that. Segmentation, so these pixels are sky, these pixels are road. And a lot of this has led to things like automating, radiology, autonomous vehicles. All were unlocked by that first wave of advance with deep neural networks. In 2015, you had 2012 to 2015, it was very hard to train a deep neural network, but then you started having frameworks. The first one that really made deep learning accessible was Keras. And then from there, really it became possible for, not just PhDs at the University of Toronto, but anybody to train deep neural networks. Then the next set of big breakthroughs, I think we had diffusion models, maybe around 2017, which is ultimately what has led to a lot of the now the generative image work. And then in 2018, of course, we had the transformer. We had the attention is all you need, and then and BERT. And since then, I think progress has just been breathtaking. Bigger and bigger and bigger models, leading to more and more spectacular results, with GPT-3 being the big milestone, and then Chat GPT being the aha moment. The consumable version of that has opened so much of the world's eyes to what's possible here.
Yeah, and I guess this is maybe this is philosophical, but do you think we've moved from an era of data science to an era of kind of AI?
So certainly, if you were to kind of classify if data scientists are, some of them are statisticians and some are bioinformaticians and some are computer scientists and machine learners, it's definitely the case that the computer scientists have won, if that makes sense. Neural networks come out of computer science. Random forest, gradient boosting machines. So all the dominant techniques really have come out of that, call it computer science discipline. I will say that it is still the case. Transformer models do extremely well on a lot of problems. They're working on computer vision problems. They're working for obviously the NLP use cases. I think they're also really good, as I understand it, for problems, proteomics and other problems like that. It still is the case that for smaller structured problems, it could be forecasting or problems more like that. It is still gradient boosting machines that are dominant. And then, this concept of transfer learning, which is so important for unstructured use cases, does not work so well for structured data more generally. So there hasn't been the breakthrough. I think the breakthroughs on unstructured data are breathtaking. The breakthroughs on structured data have, not yet materialized.
And
or
it's
not to the same extent.
you recently started Sumble and have gone from Kaggle as a platform to now as a kind of a user of different tools. What was your journey there? Like how do you decide what I think one of the big problems today is what tool do I use for what problem, and people jumping to the coolest tool, but maybe jumping over something that would work and be simpler.
Yeah,
How do you decide what to use and for what problem?
sure. So maybe just on Sumble briefly, we're a very, very early stage company. It's just me and Ben Hamner, who was my co-founder and CTO at Kaggle at the moment. Although we have a couple of new starters starting soon, and we're aiming to build a large repository for external data sets. One of the things we've been playing with is this idea of, can you extract structured information out of unstructured data? And it's been interesting. We've been playing with I guess as we've been kind of as I said, we're in very early experiment mode, but we've been trying everything from regular expressions through to GPT-4. It's been interesting to sort of see the boundaries of what techniques work well on different types of, I guess, NLP problems. So our use cases have been things like entity recognition. So that's like Jeff Bezos, the CEO of Amazon, stood down last week. If you have a sentence like that, an entity will be Jeff Bezos person, Amazon company. For extracting entities out of text, we found GPT-3, we haven't rerun this on GPT-4, but GPT-3 got an F1 score of around about 0.35, whereas training fine-tuning a Hugging Face model, not a particularly big one. We're using long form text, so we use Longformer, which is a long token version of BERT. Fine-tuning that model with about 500 labels got an F1 score of 0.85. So at least for that use case, GPT-3 wasn't quite, the performance wasn't strong. We haven't run strong enough. We haven't rerun this on GPT-4, but of course another issue is cost. It would be much too expensive across our corpus of data to do inference with GPT-4, but where it could be really useful is, I was our data labeler, very tedious, took me a heck of a long time to label our data. If GPT-4 is actually meaningfully more performant than GPT-3, and it is actually good enough, probably what we would end up using it for, while it is as expensive and slow as it is for labeling.
I feel like that's an interesting. I mean, there's a whole interesting labeling thread there. But just to confirm, like long form is kind of a transformer based. Maybe it would be in the LLM category, but just fine tuning and building it yourself on your own data set versus the general GTP4. That was the AB thing you're doing.
Yeah, exactly. And Longformer, I don't think would classify as an LLM. It's not a particularly large. It's probably a BERT size model. I actually don't know how many parameters, but it's not large. We trained it on. Let me think. Well, we fine tuned it on 1T4 GPU, and it would take us about, I think, an hour to fine tune on 500 labels, maybe less, on not a very powerful GPU. So it really was not a very large model. But what we would do is we'd take a model. Longformer was a language model, so trained to predict the next word, and we just fine tuned it. We just fine tuned it to extract entities out of our specific type of text.
Got it. One question, as we're going through this, there was one question from the community. Thought we'd answer it. which is how do you account for interpretability and explainability when when evaluating LLMs? Any thoughts there? And happy to also note what we see too.
Yeah, I mean,
Yeah,
actually, you probably have more information, more data here than us.
yeah,
It is something I worry about. We're using one place where LLMs are doing unbelievably well is summarization. So taking a large um, chunk of text and doing what we call abstractive summarization, where you're not extractive, where you're pulling a key sentence out, but abstractive, where you're sort of synthesizing what is being read. And I think it's really certainly the smaller BERT-sized models, you cannot get close to matching the performance that we get from, call it a GPT-4. That being said, I really do worry about this idea of I worry a lot about, like, is it actually summarizing what is in the text, or is it sort of drawing on some knowledge it has from elsewhere and or hallucinating? And Jason, you and I were talking a little bit before we got on about ways we might uh, evaluate whether it really is a good summary. And one of the ideas that you shared, which I really liked, was this idea that you could use another LLM to evaluate the performance of the previous LLM, which I think is something we will definitely try to get more in order to get more confidence that the summarizations are actually accurate. But I'd be curious to hear your answer to this.
yeah. I think that's one area that's growing quite a bit, which is use one LLM to evaluate the response of a second of the first LLM. So OpenAI put something out called OpenAI Open Evals, which is kind of a way to try to standardize this kind of evaluation approach for LLMs. What all they're standardizing is the prompts that you use to do that evaluation. I would say there's kind of like that one angle, which is use an LLM to help you understand your LLM's response. I would say there's one other approach which we're seeing, and it's very different than traditional explainability. Um, and the traditional, I would say traditional structured explainability slightly works by, like, you fiddling or flipping inputs and seeing the outputs, and that it's just for structured for LLMs that just isn't what you do. um, for what we've been seeing is actually extracting latent structure for those responses. And so we have some examples we've done with pretty large language models. Databricks just trained one called Dolly. It's Dollly. Kind of confusing. It's not Dolly. But there's a big there's a big one trained, and you can extract latent structure and embeddings either by sentence or by paragraph of those responses. You can follow the latent structure through. You can compare it to baselines, and with some of the stuff we'll be putting out, you can actually follow the conversation through latent space. So what are the subjects? How does it progress? A lot of the way these models learn is or understand things is in that latent space, and building tools to help understand that latent space, I think, is a powerful way of understanding how these things are how their thought processes are progressing, different ideas, how they move between ideas. I think there'll be a lot more there, early stages there.
Yep.
Um,
Certainly an open, one of the big open areas, right?
yeah. Huge open area. Uh, keeping going on some of the other comments we had was just on Sumble. I think that was really interesting. I think one of the points I wanted to highlight that I think you highlighted here, and it's a big debate across a lot of teams, is it GPT-3 or GPT-4, or do I fine tune my own internal model or train my own internal model? And I think in your case, you landed slightly on the other side. Like you have your own data, you're getting better results. Let me, very simple, smaller model, but still transformer based, still a language model. But training it could beat the general model.
That was for GPT-3, and my strong suspicion is that if we reran that on GPT-4, GPT-4 probably matches or outperforms.
Got it. Yep.
That wasn't even 3.5; it was 3. My strong suspicion is that GPT-4 matches or outperforms. Even so, we still would need to train our own traditional or fine tune our own model, because GPT-4 is too expensive and too slow. And so the next step for us, assuming GPT-4 performs as I expect, and that it would produce an F1 score better than what we get from our human raters or our own fine tuning, then we would use it for labeling, and then we would train a model to match those labels. And then eventually, I could totally imagine if GPT-5 was fast enough and cheap enough that we wouldn't bother training models. So it's sort of hard to predict the arc of progress.
Yep.
There's certainly a direction that I know a lot of people are working on, which is exciting, which is around distillation. So you take a large language model and then you ask it consistently the same question, like help extract the name of people out of this text, as an example. You don't really need the full power of a large language model in order to do that fairly repetitive task. But it's nice not to need to have to train a model from scratch. And so, an area that a lot of people are working on are, okay, let's send the LLM 50 examples of how to extract a person out of your specific type of text. And then what they'll do is distill the large language model to just take the portions of it that are relevant to your task. And I think that's an exciting area of investigation, because hopefully you get the performance and of an LLM and the simplest, you kind of avoid really needing to train a model, but you get the cost and inference speed of a smaller model. So that's a direction that I'm keeping an eye on and could give us the best of both worlds, right?
I thought I'd do one hot take at the end here. You probably have 60 seconds to answer, and it's okay to punt on this too. But what you just Kaggle was acquired by Google. You've been watching Google for a while. I'm kind of surprised that OpenAI feels like they're ahead. I mean, Google should be ahead. Like, what's your take on the OpenAI versus Google? I mean, amazing team there at Google, but why does it feel like OpenAI has leaped ahead, and how is that possible? And you have 60 seconds to.
Yeah, totally. I mean, Google and OpenAI are both chock full of incredible talent.
Yeah.
One challenge that Google and Microsoft and other large companies have is they have legacy businesses to protect, and I also think a unit of time that an engineer at Google is spends doing something is less efficient than a unit of time that an equivalently talented engineer at a place like OpenAI can do things. So I think Google has a strategy tax is one, and just the bureaucracy of a large company slows them down. So given equivalent talent, it's not surprising to me that OpenAI does feel like the leader.
But I'm surprised. I still, Google's amazing. It'll be fun to watch what comes out of that team soon. Well, I think that's we're probably coming to time here. Thank you all for joining us. Thank you, Anthony, for joining us here. Awesome conversation, and enjoy the rest of the Observe, and appreciate the time.
Thanks for having me.
Great. Awesome.